Today I'm going to be helping you evaluate whether or not graphs are accurate. When evaluating a graph, your job is to ask, does this picture accurately communicate the numerical information in the data? A graph is well constructed when the visual impression matches the underlying data. So first we're going to ask, what is a graph? Well, a graph is a statistical visualization summary of a data set that displays numerical information in a form that's easy to input and compare. An accurate graph preserves the underlying data relationships, meaning that the sizes, lengths, positions, and proportions shown in the graph correspond to the actual values. When a graph is constructed correctly, the conclusions a viewer draws from the picture are the same conclusions you would obtain by just looking at the raw data. So when evaluating a graph, first we're going to look at the scales and the axes. We're going to make sure that these are appropriate and evenly spaced so that there's equal visual distances and they represent the actual numerical values. Axes are the reference line on the graph. The horizontal line is called the x-axis and the vertical line is called the y-axis. Scales are the numerical markings along the side of the axes. The next step we're going to take is verifying that both axes are clearly labeled, including the variable names and their units. These usually go below the x-axis and next to the y-axis. Units are things like dollars, years, or percentages that were evaluated in the data. The units should remain consistent throughout the graph. Mixing units or changing scales without notice is often how mistakes in graphs happen. Finally, we want to make sure that our graph type matches the type of variable that we're looking at. Bar graphs are usually used for categorical data. Histograms are usually used for quantitative distributions, and line graphs are used for changes over time. Scatter plots are used for relationships between two quantitative variables. Usually a well-designed graph satisfies all of these criteria, allowing a visual impression to reflect the underlying raw data. This is my first example, and for the first example, we're going to suppose that sales increased from 100 to 110 units. A proper bar chart is always going to start at 0. So here you can see that there's a 10% increase, or 10% increase appears in the data when the axis begins at 0. It looks modest here. However, if the axis were to begin at 95, the second bar would appear dramatically taller, even though it's still only increasing 10%. This is a classic example of how graphs can be misleading. Another common problem is using pictures whose area grows faster than the data. If a pictograph doubles both the height and the width of an icon to represent a doubling in value, the area will become 4 times as large, exaggerating the change. For example 2, it is another example of a correct graph. This graph is correct because the time is placed in chronological order on the x-axis. The axes are clearly labeled with appropriate units in degrees Fahrenheit, and the scale is uniform. A line graph is a proper choice for showing how a quantitative variable changes over time. The visual trend accurately represents the underlying data value. For my third example, this is an incorrect graph. This is not what your graph should look like. This graph is incorrect because the line graph implies that the x-axis values are in a meaningful order, but scrambling the months, the graph creates a zigzag pattern that reflects fluctuations and that never actually occurred in our raw data. The usual impression no longer matches the true, steadily increasing temperature trend in our raw data. As a rule, whenever you are looking at a graph, I would say just ask yourself, if I ignored the picture and only looked at the numbers on the graph, would I still come to the same conclusion that I am just looking at the numbers in the raw data? If your answer is no, then the graph is misleading. So to verify graphs, I would say a good checklist is to first verify that the axes and scales are labeled correctly and the axes are labeled correctly and the scales are evenly spaced out. Next, check whether the graph type matches the data, and then ensure that visual elements like bars and symbols are proportional to the actual values. After that, look for omitted data, distorted axes, and unnecessary 3D effects. And then by consistently comparing the visual impression with the numerical values, you can quickly determine whether a graph represents the data honestly. A valid statistical graph should represent the data by preserving the true distribution, relative size, and trends present in the underlying numbers. Its purpose is to help the viewer understand the data accurately, not to exaggerate, hide, or distort important features. When a graph is constructed with appropriate scales, labels, and formats, the conclusions drawn from the picture graph are also the conclusions that are drawn from the data themselves. Thanks.